This week, we're moving on from ANOVA, and we're going to start talking about multiple regression. And we're going to start with univariate multiple regression, but we're going to think about it in a new way because now we're going to look at it using matrix notation. So we should all be familiar with what a multiple regression model looks like. And so it has this structure where you have p predictors, where each is associated with a beta coefficient, and then you also have an intercept beta 0. And an error term epsilon. So when we have n observations in our data, our sample size is n, we can write each observation as, or each y, as being a function of the regression model with each beta multiplied by the value of each predictor, and then some error for that given observation. And so this is a way of decomposing each individual y into a linear function of the betas and error. So we can actually rewrite this in matrix notation. And this is both convenient because it's compact, and it's also important to know about because you'll see this in, or this sort of structure in papers a lot of times. In fact, you'll often see an extension of this when you see HLM models written out, which are just a slightly more complicated version of this. But here we're just going to look at regular regression. So here we have bolded everything up. So y is actually a vector. It's an n by 1 vector representing the response variable. Z is an n by p plus 1 design matrix. It's what we call a design matrix. So it's actually the p predictor variables and observations of the p predictor variables. And then there's actually the first column is an extra column of all ones, and we'll see why that is. So B is also a p plus 1 by 1 vector of beta coefficients. So this includes the intercept. That's why, again, it's p plus 1. And this is also why we have the extra column of ones in Z, which again, we'll see in a second. And then epsilon is just an n by 1 vector of residuals or error. So this is the way we would visualize the matrix form of a regression model. And so you see what we're doing is we're multiplying this design matrix where we have all of our x's by the betas, but we need this extra column of ones because it's what we multiply the intercept by. So this is just saying every row also gets the intercept added in. It's not multiplied by anything. It's just multiplied by 1. And then we have our error as well. So multiple regression uses a technique called least squares to estimate the parameters of interest. And so the least squares algorithm is a way of minimizing squared residuals, so the squared epsilons. So you'll sometimes hear this referred to as a loss function. So a loss function is the type of error that we want to minimize. It's how we define what our best estimate is. So in regression, the loss function we're using is least squares because we're trying to minimize squared error. So another way to think about this is how we're choosing to minimize the difference, or a loss function is how we're choosing to minimize the difference between our actual y's and the y's that are estimated by our model. And so in this case, we're estimating, or we're minimizing the squared difference between our actual y's and our estimated y's. So you may have gone through a proof of this in class, I'm not sure, or in lecture, but we can find the least squares optimized betas, which minimize the sums of squared errors with this formula where we take the design matrix transposed times itself, invert it, multiply by the design matrix transposed times y, and that gives us our estimated betas. So let's look at an example, a very simple one that we can do sort of by hand. So this is in the book, and here we have an example where we have one response variable y and one predictor variable x1, and the sample size is just 5, so that we have 5 observations. So we're just going to get our betas by plugging into this formula, and we'll go step by step. So first we need to define z. So what is z for this example? So z is always going to be all of your predictor variables with an extra column of ones tacked on the front. So we have one predictor variable here. So we're just going to tack on a column of ones. So that's our z matrix, our design matrix. So then we need to define all our. I'm not gonna write out all the actual matrix steps here. I'm just gonna do the rest of this in R. So here I'm gonna start by defining X as my predictor variable. I'm going to define Y as my outcome variable, and then I'm going to get my Z, I'm just going to slap a column of ones onto the front of my predictor variable to get my design matrix. So now I'm going to plug everything into this formula. And again, I'll go step by step here so we see how all the matrices conform. So the first step is we need to take Z transpose times Z and invert it. So Z is n by p plus 1. So in this case, that's a 5 by 2. So transposing a 5 by 2 gives a 2 by 5. So we're doing a 2 by 5 by a 5 by 2, which is going to give us a 2 by 2. So there is our first step where we get our 2 by 2. So now, again, we need to take what we just got, our 2 by 2, and multiply it by Z transpose. So again, we're going to note that Z is 5 by 2, so we're going to have a 2 by 2 by a 2 by 5. So that's going to give us another 2 by 5. So here we multiply our first step, the Z transpose Z, and we're going to multiply it by the transpose of Z again. So that's going to give us our 2 by 5. And then finally, our Y is n by 1, which in this case is 5 by 1. So we have a 2 by 5 times a 5 by 1, so that's going to give us a 2 by 1. And that 2 by 1 is our regression coefficients. So this is 1 is the intercept, and 2 is the coefficient for our predictor. And of course, we can check our work just by using the LM function in R and checking the coefficients. So I don't need to define the data here because Y and X are separately defined objects. But here you see that I get the exact same results. So we can also use the regression framework to understand ANOVA. And this is especially important if you're going to do programming in R, since R really uses this as how it computes ANOVA. So here we're going to consider a one-way ANOVA, where our response variable Y is an 8 by 1 vector. So this is the dependent variable. And there are going to be 3 groups. So the first three observations are group 1, the next 2 are group 3, or group 2, and then the last 3 are group 3. So we're going to write our design matrix like this, or we could write our design matrix like this, where we have a column of ones, then we have a column where it's 1 or 0 for the first group, then a column where it's 1 or 0 for the second group, then a column where it's 1 or 0 for the third group. So here you see the first 3 observations are group 1, then group 2, then group 3. So why wouldn't we want to do it this way? This isn't the correct way to do it, but it is an intuitive way. So the reason is that now if we do it this way, each column is linearly dependent. So what we can see, for example, if we look back, column 4 is equal to column 1 minus column 2 minus column 3. So here we have 1 minus 1 is 0, and then here we have 1 minus 1 is 0, and here we have 1 minus 0 is 1. So really, any single column can be written as a function of the other 3 columns. So that's why we don't want to do this. Conceptually, what this is saying is that all of the information we need is carried by any 3 of the columns without the 4th. We don't need the 4th column. Computationally, what it means is that if we square our design matrix, we take Z transpose Z, we're going to get a singular matrix, meaning it cannot be inverted, and meaning that it has a determinant of 0. So this is not what we want. So here's how we can actually do this in a way that would work and give us equivalent results to our ANOVA, in fact, give us an equivalent model. So we're going to take, here's just what we're going to call our Y value, and this is also an example in the book. So this is our response variable. And here's how we're going to define our design matrix. We're going to drop one of the columns. So here I'm just going to drop X1. And so effectively, this is calling X1 our reference group, and then we're dummy coding. So if these 2 columns are both 0, then that means it's group 1. If column 2 is a 1, it's group 2, and if column 3 is a 1, it's group 3. And so I can then go and get my my 3 coefficients. And so how would we interpret these? So this is, remember, this is dummy coded. There are other coding schemes that would work. Dummy coding is just the most common and intuitive. So what this is telling us is that the mean of group 1, which is the reference group, is 8. That's the intercept. The mean of group 2 is then the intercept minus the second coefficient. So 8 minus 7 is 1. And the mean of group 3 is 8 minus 6 equals 2. And you can feel free to verify these results. And of course, we can check that the actual AOV function gives us the same results. And indeed, here it does. The intercept is 8. And we get a -7 and a -6 for our 2 group coefficients. So this is, now we're going to talk sort of about one of the things we looked at last week. And so in one-way ANOVA, we can actually drop the intercept instead of dropping the one of the reference groups, the reference group dummy variables. So in this case, we're dropping the intercept, and we're going to have, so the first coefficient is 1 for group 1 and 0 otherwise, and then the 2 and 3 are the same. And this can help make our results a little bit more interpretable, or a little bit more directly interpretable in one-way ANOVA specifically. So the reason is, if we do it this way, now each coefficient is actually going to be the mean, just directly the mean of each group. So the first coefficient is the mean of group 1, the second one's the mean of group 2, and the third one is the mean of group 3. And so this is nice and straightforward and easy. We don't have to do any subtraction to figure out what the means are. It just gives it to us straight away. The reason we don't do this more commonly is it doesn't actually work once you have more than one grouping variable. So if you have a two-way ANOVA, suppressing the intercept isn't going to help us. Can anyone sort of think about why before we go ahead and look at it? So the reason is you still only ever have one intercept, and that accounts for all the different grouping variables. So they all go into the same design matrix. So let's think about how we're going to have to write our design matrix in a two-way ANOVA, where each factor has 3 groups. So here I just put the reference for the what group, how you'd code each group here in the first column. So then we get our first column of, which is our intercept. So group 1 plus group 1 is going to be all zeros. Then group 1 plus group 2 is going to have a 1 here. Group 1 plus group 3 is going to have a 1 here. So then group 2 plus group 1 is going to have a 1 here, and then all zeros. And so you can sort of see so on and so forth how this goes. Now, notice that this only has 5 columns in it. It doesn't have 6 columns across the 6 groups. So even though there are 6 actual potential grouping factors, there are only 5 columns in the design matrix. And this gives us all the information we need to estimate the model. If we had an extra column, we would be over parameterized. And again, we would run into the linear dependence issue that we saw before. So you actually can't write a two-way ANOVA where you have 1 coefficient for each group. You have to drop 1. Otherwise, it won't work. And so that's why it's a little bit more straightforward just to keep the intercept and then do the dummy coding this way. And so that's multiple regression and ANOVA using regression methods and matrix notation.